Okay, we're beginning our examples of finding relative maximums and minimums of functions. And let me remind you that when we're tested over this, we're not going to be able to use a calculator. So make sure that you can do this work without the use of a calculator. A calculator might be useful to kind of test your hypothesis after you're finished with the problem. Now, in the statement of this problem is find the relative extrema of f of x equal 2x cubed minus 3x squared minus 72x plus 15. And when we see it put that way, it means find any relative maximums and find any relative minimums. It's not telling us to find a specific one, find any of each type. So remember, number one thing that we're interested in are critical numbers, because critical numbers are the only places that these maximums and minimums can occur. Now, to find a critical number, we have to know what? We have to first find the derivative, okay? Because the critical numbers happen where the derivative is either 0 or undefined. So when we look at this problem, of course, we can calculate the derivative fairly rapidly. What we're going to get 6x squared minus 6x minus 72. Now, because this is a polynomial, it's going to be defined everywhere, so there's no place where the derivative is undefined. So we'll need to consider the derivative being undefined. It's defined everywhere. I'm just making a point of that right here. I'm worried about that. But we are concerned about where the derivative might be 0. And of course, what we're doing is we're setting the derivative to 0 and solving for the appropriate x's. Okay, set to 0 and solve for what x's cause that to happen. Now, I'm noticing that 6 is a common factor, and so I could actually take both sides of this equation and divide by 6. And of course, when I divide, and I'm going to try to save some space, and so I'm going to move over here as I'm doing this. When I divide 6x squared by 6, I can just get x squared. And when I divide 6x by 6, I just get 6. And when I divide 72 by, I just get x, my bad. Just get x. And when I divide 72 by 6, I get, 12. And so my equation becomes x squared minus x minus 12. So this looks like this will be fairly easy to solve. I think I can factor on the left side, so I'll attempt that. Yes, it looks like I can. I'm going to try a minus 4 and a plus 3. And of course, x times x is x squared. Negative 4 times 3 is that negative 12 at the end. And in the middle, I get a negative 4x plus a 3x, which is, of course, negative x. And so here the solutions are the x values that would cause the first factor to be 0, and that would be 4. And the x values that cause the second factor to be 0, and that would be negative 3. So we have two critical numbers. Okay, let's make a point of that up above. Our critical numbers are, I'm going to put negative 3 and 4. Okay, and the reason I wrote them in that way, because the next thing we need to do is test for a change of sign across a change of sign of the derivative. At the critical numbers. So this is basically what the first derivative test is about. Okay. First derivative test. And here's the way we're going to do that. We're going to, this looks very similar to finding out when a function is increasing and when a function is decreasing. So I'm thinking more or less of this being like the x-axis is really what I'm doing. And so I want to put my two critical numbers on there. Negative 3 is one of them. And the other one is 4. I just need some space in between. There's nothing significant. I just need the relative positions. And so what that does is that cuts the number line into 3 intervals, doesn't it? It's the values that are less than negative 3, so that's negative infinity up to negative 3. And the values of x that are between negative 3 and positive 4, so that's the interval negative 3 to positive 4. And then there's the x values that are beyond 4, so that's the interval from 4 to infinity. Now, what we're going to do, again, is we're looking for a change in sign of the first derivative. Okay, that's what we're going to be doing. And so I'm going to set it up this way. Let's make one more column out here. And now, let's say in here is the sign of f prime of x. Now, we've done this kind of situation. We've dealt with this before. In the interval from negative infinity to negative 3, we need some x value. And it really doesn't matter what x value we choose. Negative 10 would certainly fit the bill. Now, I don't really care about whether the derivative, the value of the derivative, but I care about the sign of the derivative. Because remember, the sign can only change at these critical numbers, negative 3 and 4, because that's what's related to where we change directions, and that can only happen at critical numbers. Okay? So f prime of negative 10, well, what would we do? We'd go up and look at the derivative function, and of course, this is the derivative function. And not any simplified version of it, that's the derivative function. So we need to put negative 10 into that function. So 6 times negative 10 squared minus 6 times negative 10 minus 72. Okay, well, what we see that we have here is in the first position, we have a positive 600 and then plus 60 and minus 72. And again, I could care less about the value. I only can tell, all I really need to worry about is I can tell that it's positive. So the first derivative is positive in this interval from negative infinity to negative 3. Now, just kind of as a little guideline here, that means the function is going up, doesn't it? See, that's what that means. The function is increasing. Okay? So we kind of get that idea, and I'll just make that note here, then the graph of f of x is increasing. Just like what we did before, except we're going to get new information. Now, in the interval in the middle, from negative 3 to positive 4, we need to choose some x value, and certainly 0 would fit that category. It would be in between negative 3 and 4. So we calculate f prime of 0. And when we do above, we'll see very easily, well, let's just go through it. It has 6 times 0 squared minus 6 times 0 minus 72. And of course, that's just going to be 0 minus 72, which is negative 72. But the number is not important. It's the fact that it's negative. So the sign of the derivative is negative in the next interval. And this is exactly what we were talking about before. We're seeing the sign of the derivative change from positive to negative across the critical number negative 3. That means we have something happening. So if it's positive, it's increasing. If it's negative, the graph is decreasing. And we might illustrate that this way. Well, if it goes from increasing to decreasing, that means we have to have a relative maximum happening right there. Okay, we change from increasing to decreasing. Okay, well, we'll continue this process. Now we look at some value, some x value between 4 and infinity, and of course x equal positive 10 would fit that, and so we calculate f prime of 10. When we do, we'll have 6 times 10 squared minus 6 times 10 minus 72, which will end up being 600 minus 60 minus 72. But clearly that's positive. Okay? Now, we see that we change signs again. See, across the critical number 4. When we went across 4, we had the sign of the derivative change. So that means we have something else happening. Whenever the sign changes, we have a minimum or a maximum. Now remember, in here we're decreasing, and now it's telling us that we're increasing. Oh, I didn't put that in here. We're increasing, aren't we? Well, if we change from increasing to decreasing, that means at 4, see, at x equals 4, we must have a relative minimum. It bottomed out and started going back up. Relative minimum. Now, we're not really done here, though, okay? We found the x value for where we have a relative, say this relative minimum at x equal, a relative maximum at x equal -3. But we still have to find out what the relative minimum is and what the relative maximum is. Okay, so let's first look at this relative maximum. See, the relative maximum is the y value f of -3. So we're talking about the original function f. Okay, original function f. And what we know is when x is -3, we change from increasing to decreasing, and so that y value is the maximum in the area. Okay, so to answer this question, though, what the relative maximum is, we actually need to do the calculation. So we'd say, okay, we'll take the function f of x, which is 2 times x cubed, and so we'll put a -3 in for x, and minus 3 times x squared, so we'll put a -3 in for x, minus 72 times x, we'll put a -3 in for x, and I've run out of room, haven't I? And then we say plus 15, my bad here. And when we do all that calculation, we're going to get 150. And so this 150 is the relative maximum. That number is the relative maximum. Now, for the relative minimum, we need to do the same kind of thing. Minimum. 4 is not the relative minimum. It's the x value where that occurs. It's the y value of that point that's the relative minimum. So we have to calculate f of 4. And remember, that's the original function. So let's say 2 times 4 cubed, minus 3 times 4 squared, minus 72 times 4, and plus 15. And we have to do some calculations. I'm convinced you can do that. And when we do all those calculations, we'll get a value of -193. So -193 is the relative minimum. Okay, now, I think what I'm going to do next is I'm going to get up a graph of this function, and so we can see that what we've just accomplished, because I think that will be very useful to us in the big picture of things here.
Here you can see the graph of the function. Remind you of what that is. It's f of x equal 2x cubed minus 3x squared minus 72x plus 15. And as we were analyzing this, we came up, if you recall, with critical numbers -3 and +4. And that's where the derivative was 0, so we were expecting a horizontal tangent line at those x values, and that horizontal tangent line usually is associated with a relative maximum, a hump going up and then down, or a hump going down and then up. So here's the -3x value, and it corresponds to the point up here, which is a relative maximum, and the 4 critical number, which of course corresponds to this valley down here where we have a relative minimum. and we found out the relative maximum was this y value 150. So that makes sense what we were doing. We put -3 into the function to get this y value of 150. So 150 is the relative maximum. That's the highest place around on that part of the graph. And then we found below that at 4, the relative minimum was actually -193. And you can see on our graph, certainly at this position down here, and it keeps popping up on us, yes, that looks like that's approximately, that y value is approximately -193. So this is to exactly what we saw happening with our analysis. So we'll go to the next problem.
Okay, well, we're ready for our next problem. Find the relative maximums and minimums for the function f of x equal x to the 4th minus 2x cubed. Now, we really don't know if it has any relative maximums at all. We really don't know if it has any relative minimums at all. We certainly don't know how many of each. So we're just in for the ride to analyze this graph. Now, I'm going to start this off by reminding you, and this is the thing I want you to recognize and travel with, that is that relative maximums and minimums can only occur at x values that are critical numbers. Okay, so let's not forget that idea. So that means the first thing we have to do is find the derivative, because that's how we'll find the critical numbers, isn't it? And so we look above, and we can calculate the derivative very easily again, because it's a polynomial, so we get 4x cubed minus 6x squared, don't we? Next thing we do then is we find the critical numbers. And after that, we'll test. Well, there's two kinds of critical numbers. Okay, there's critical numbers about where the derivative is 0, and we can have a critical number also anytime the derivative is undefined. But once again, in this case, the derivative itself is a polynomial, so it's never undefined, so we're not concerned with about that. We're just concerned about where the derivative, which is 4x cubed minus 6x squared, is 0. And so we need to solve this equation, and we look here, and we'll use any technique we can, and factoring was a common technique. I'm noticing that 2x squared is a common factor, so I'll factor out a 2x squared. When I factor out 2x squared, I'll have what? 2x minus 3 left. Now notice I didn't divide out this time. I suppose I could have divided out a 2, but you can't divide out a variable amount, because you don't know whether that variable amount has the value 0 or not. When I'm dividing by a number, I know whether that is 0 or not, so that's not a big issue. But it is when we have a variable. So I didn't divide out an x squared. Now, what we do next, of course, is we take each of these factors and we set them to 0 separately, and we solve the resulting equation. And of course, in the case that 2 times x squared is 0, that implies that x has to be 0, doesn't it? And in the case that 2x minus 3 is 0, then the first thing we'll do is add 3 to both sides, and then we'll divide on both sides by 2, and so we'll get x is equal to 3 over 2. Now, these are the two critical numbers. And these are the places that we might, I can put that, have a relative maximum or a minimum. Okay? So, what are we going to do to find out? Well, we're going to look for a change in the sign of the derivative across these two critical numbers. So we begin our little testing. See, let's do that over here. Right here. And suppose, okay, so we're going to test the sign of f prime of x. And we're concerned about what? Well, and our smallest value is 0. And then the next value we have is 3/2, 3 over 2. And that creates 3 intervals for us again. From negative infinity up to 0 is one interval. From 0 to 3 over 2 is a second interval. And from 3 over 2 to infinity is a third interval. And so we just need to test the sign of f prime of x in those intervals, and then we'll decide whether we have a relative maximum at x equals 0, or if we'll have a relative maximum or minimum, either one, at x equals 3/2. So, sorry, this is x equals 0 there. Okay. Well, to go off and either do this on our scratch paper or we can do it right here, let's remember that f prime of x is 4x cubed minus 6x squared. And so we need to find some value in the interval negative infinity to 10 that we can check. And so negative infinity to 0. So I suppose negative 1 would work just fine, wouldn't it? So we calculate f prime of negative 1. It'll be 4 times negative 1 cubed minus 6 times negative 1 squared. Well, that's going to be a negative 4 and a minus 6, which is negative 10. So the sign is negative in this interval. Okay, so now we're looking for a value in the next interval. Now the 3/2 is 1.5. So x equal 1 would certainly be a valid choice of x there. So we'll calculate f prime of 1, which will be 4 times 1 cubed minus 6 times 1 squared. And when we calculate here, we get positive 4 minus 6, which is negative 2. Okay, well that's negative also. We didn't see a change in sign. We've stayed negative. So we don't have a relative maximum or a relative minimum at x equals 0. Well, let's continue. In the interval from 3/2 to infinity, we need to pick an x value. Well, 3/2 is 1.5, so we could pick 2 or 10 or whatever we want to do. We'll calculate f prime of 10. So that would be 4 times 10 cubed minus 6 times 10 squared. Well, 10 cubed is 1,000, so this is 4,000 minus 600. And I don't really care about what number that is. It's clearly positive, isn't it? Okay, so in this interval, we're positive. Now, let's just kind of, the graph of f, let's just kind of boil things down here. The graph of f here, we know is decreasing in this interval, and it's decreasing in this interval. But it's increasing in this interval. And it's this change in this sign from negative to positive that we're worried about. It's decreasing, and then over here it's increasing. So that tells us right here at x equal 3/2, we have what? A relative minimum. A relative minimum occurs. And it doesn't tell us what the relative minimum is, but it tells us when it occurs there. And here what we see is that we're decreasing, and we continue to decrease in these two intervals, don't we? So we're decreasing and decreasing, no change in sign, we didn't turn around, and so there's no relative minimum or relative maximum at x equals 0. Okay, we don't have either one of those situations. So in this case, to answer the question, okay, we can immediately go to and say there are no relative maximums. but there is a relative minimum. And we say the relative minimum is, well, it's a number, and it's the number we calculate by putting 3 halves into the function f. Now notice, this is not the derivative, not f prime, it's f. Use f, because we're talking about the function f as a minimum. So we go to the original function, which is x to the 4th minus 2x cubed. So we have a 3 halves to the 4th power minus 2 times 3 halves to the 3rd power. I haven't done this. I hate to have to do all this in front of you, but I guess I need to. When I take 3 halves and raise it to the 4th power, I'm actually going to get 81 over 16. And when I take 3 halves and raise it to the 3rd power, I'm going to end up with, what is that, 27 over 8. And so that's going to be 81 over 16 minus, actually, we could say, what, 27 over 4, couldn't we? But now I need a common denominator to be able to combine these. And so I'll have to change the fraction 27 over 4 to 16. So that means I have to multiply by 16 on the, 4 on the bottom and 4 on the top. 4 times 27 is what, 80, and 28 is 108, I believe. And so we get, what is that, negative 27? Negative 27 over 16. Okay, negative 27 over 16 is the relative minimum. Relative minimum is, now remember we calculated it by putting the x value where that occurs into the function. The relative minimum is negative 27 over 16. And I suppose we could write that as a mixed number, okay? Now we won't do that in our homework, but when we go and look at the graph in a moment, it might be useful. As a mixed number, what is that? That negative, 16 goes into 27 one time, negative 1, and what's the remainder? 11. So negative 1 and 11 sixteenths. That's almost negative 1 3/4 roughly. Okay. Well, what I'm going to do is bring up the graph of this so that we can see what it looks like before we go on to the next example to put it all together. Okay.
Well, here we see the graph. I've got it miniaturized. So just to remind you, this is the graph of f of x equal x to the 4th minus 2x cubed. And we found two critical numbers, x equals 0 and x equals 3 halves, which is 1.5. Now, let's expand that so we can see it. X equals 0, of course, is this value, and x equals 3 halves, or 1.5, is this value. Now, the reason those are critical numbers is because the derivative was 0. So at this x value, x equals 0, if you look at the tangent line, it'll actually cut right across here. And so it is a horizontal tangent line when we're talking about that point. Now, of course, the point over here, the tangent line would run this way. Point over here, the tangent line would run this way. But right here, the tangent line is horizontal. And of course, down at this position, the tangent line is horizontal, and that's where x is equal to 3 halves. Well, when we checked out the derivative, we found out that the function was decreasing on the left side of 0, and it was still decreasing on the right side of 0. And that's the reason we decided we didn't have a relative maximum or a minimum, either one that went with the x value of 0. But when we looked at the x value of 3 halves, 1.5, on the left side we found the function was going down, and on the right side we found it was going up. So we concluded that we had a relative minimum. And that relative minimum occurs when x is 1.5 or 3 halves, and the value of that minimum is the value that's this y over here. And we said that that was negative 27 sixteenths, or not quite, negative 1 3/4. And that looks just about right, doesn't it? So we found all that information without ever knowing what the graph itself looked like. Okay, well, let's let's begin the last part of this.
Okay, well, we're ready for our next problem.
Well, to close out this part, we'll have some other problems in a moment, but I want to drive home this idea. As you can see, the title of this little slide, critical numbers don't ensure relative maximums or minimums. I mean, you see up above, but they can't occur anywhere else. The only place a minimum or a maximum can occur is at a critical number. And here we just happen to see a couple of scenarios where we have critical numbers but no relative maximum or a minimum. And in this first example, the critical number is 0. And the idea here is at x equals 0, we have a horizontal tangent line, although it's not turning around, so we don't have a maximum or we don't have a minimum, either one. So just because you have a critical number doesn't mean, and the last example we saw was of this type, wasn't it? Doesn't mean that we actually have a maximum or minimum. That's just the only places they can occur. Now here's another example where the critical number is 0. Now in this particular example, the critical number is 0 because the derivative of the function is undefined at x equals 0, and you could verify that if you wanted to. And so in this case, what's really going on is if we look at the tangent line at x equals 0, is actually completely vertical. And of course, we know a vertical tangent line has an undefined slope, hence that's the reason we know that the derivative is undefined there. We could actually go and find it. So here again, though, we have a critical number where the derivative is undefined, but we don't have a maximum or a minimum. So summarizing, as you see at the bottom of the screen or the bottom of the slide, all relative maximums and minimums occur at critical numbers, but not all critical numbers have or give a maximum or a minimum value. That's the end of this part. In the next part, we'll have a few more problems.